So let me refresh again about the NMR because there is some rotation of the hydrogen. Why use hydrogen? Why use carbon? This presentation is prepared for the theory of NMR. NMR stands for nuclear magnetic resonance. This is the last subtopic chapter of the technique of analysis chapter 29. Okay, in NMR, we are not able to see molecules. The molecules are very, very small, but we can see the NMR showing the structure of the molecule because those molecules will give rise to a specific spectrum. The spectrum is already written on the data booklet that we need to see the result and then in which spectrum the molecules correspond to. Next, NMR. We know NMR stands for nuclear magnetic resonance. Okay, this one it is very common used in analytical technique for organic compounds. It is based on the fact that the nucleus of each hydrogen atom in an organic molecule behaves like a tiny magnet. The nucleus of a hydrogen atom consists of a single proton. This proton can spin. The spinning motion of the positively charged proton causes a very small magnetic field to be set up. In, in NMR, we put the sample to be analyzed in a magnetic field. The hydrogen nucleus or proton which either line up with the field or against the field by spinning in the opposite direction line up against it. There is a tiny difference in the energy correspond to the energy carried by the waves in the radio waves. Okay. In NMR, the nucleus flip between two energy level. Okay, so this NMR can be based on the hydrogen atom, also can be based on the carbon atom. And then why is there TMS? TMS is a standard compound. Because TMS is an inert, it is volatile liquid that mixes well with the most organic compounds. The formula is SiCH3O. So it is because all the hydrogen are equivalent. They are in the same environment. So this tetramethylsilane gives only one sharp absorption, which is called a peak. This peak is at higher frequency than most other protons. All the other absorptions are measured by their shift away from the TMS line on the NMR spectrum. This is the spectrum is called as chemical shift and also measured in units of parts per million. The size, as I told you, the NMR can be measured based on the hydrogen and carbon. Why is it hydrogen? There is a tiny difference in the energy between the oppositely spinning hydrogen nucleus. This difference corresponds to the energy carried by the waves in the radio wave range of the electromagnetic radiation spectrum. Only atoms whose mass number is an odd number, example like hydrogen 1 and carbon 13, absorb energy in the range of frequencies that are analyzed. The size of the gap between the nuclear energy levels varies slightly depending on the other atoms in the molecule. It is called as the molecular environment. Therefore, NMR can be used to identify hydrogen atoms, one in different parts of molecule. Set the next slide. Next slide. Nucleons have spinning. As we know, there is a spinning, and then this spinning will create a magnetic magnetic field that should be analyzed. And then this one, like in process of MRI, analyzing the organic molecules, magnetic resonance would be a very little value in chemical analysis if all hydrogen atoms are absorbed at the same frequency of radiation. The electron cloud around the hydrogen atoms partially screens the nucleus from the external magnetic field through the diamagnetic effect. The electrons within molecules, both bonded and non-bonded electrons, are usually paired. That is, they occur in pairs of electrons spinning in opposite direction. The molecule is placed in an external field. The electron pairs rotate in their orbits in such a way they produce a magnetic field, which opposes the external field. Okay. This phenomena is called as diamagnetism. The effect is to shield nearby protons from external field. This in turn reduces the frequency at which they absorb energy when they flip from the lower to the higher energy state. Okay, this is the direction of the rotation of the electron pair in the orbital, and this is the magnetic field, which is different to this one, the spinning. However, a proton is near an electromagnetic atom within a molecule. The bonding electrons are drawn away from the proton to the electronegative atom. The proton is less shielded from the external magnetic field, and hence it absorbs the radiation at higher frequency. The effect is pronounced if the proton is attached to a benzene ring. This will have the effect on the localized pi electrons in the ring that create strong
Cor, it's
dynamic
putus-putus again.
effect, which is
Putus-putus.
Yeah, yeah.
How about
opposing the
now?
external field.
Still a bit.
Still a bit.
And then there is a chemical shift. There is a chemical shift. What is the meaning by chemical shift? Okay, chemical shift is the thing that the line produced by the NMR spectrum and for all the other oxygen are measured by their shift away is called shift. Is measured in parts per million. And then in order to measure, we must use a compound which is a standard is called as TMS. In the first slide, I already explained why do we have to use TMS, because all the hydrogen in the MS they are in the same environment, and there is energy here So energy of the spinning of the pair of electrons. Okay. Next, as I told you, there is a hydrogen environment and there is a carbon environment because both of them
Teacher, putus-putus,
have
teacher.
will have an odd number. Okay. Frequency of energy needed.
Okay, was it putus-putus?
Yeah, quiet.
Yeah.
Yep.
Okay, let me
Post it in
explain.
YouTube, teacher.
Hydrogen atoms that are in different positions. The flips needs low frequency energy and then high frequency energy to flip here. So high frequency energy released when it flips back. And then here, this is the hydrogen. This is hydrogen. It needs high frequency energy to flip. And then over here, needs low frequency energy. And this one is called to be the hydrogen in two different environment. This is one environment, this is the second environment. All the hydrogen in here, they are having the same environmental environment. Okay. And then here, so the energy tells the portion of the hydrogen in the molecule. How do we see it? We have to use our data booklet. There are different types of NMR. First, there is a low resolution NMR and there is a high resolution NMR. A low resolution NMR shows a single peak for each non-equivalent hydrogen atoms. For example, in here shown in the example of ethanol. This is there are three hydrogen here, three hydrogen environments, not three hydrogen atoms, three hydrogen environment. One is CH3, the three hydrogen in the one environment, and second there are two hydrogen in the attached to the carbon in the middle, and then there is one hydrogen attached with the O. Okay. The area under the peak tells us the relative number of hydrogen atoms responsible for the chemical shield. The largest peak will be from the CH3 hydrogen atoms here. The middle peak from the CH2 hydrogen atoms, and the smallest peak is from the OH. This is the example I screenshot, the example from the data booklet. On the data booklet, it is written on here. I use data booklet. It is on this soft copy, page 13. This one is based on the hydrogen environment. So we can check this one, alkanes. This is correspond to the chemical shield at 0.9 until 1.7. And then this one, all the structure and also the functional groups of each organic molecules. Now, let's go back to the theory. This one, we can see here at the peak 1, around 1 here, correspond to the CH3. Correspond to the CH3. How come it is like that? Let's see this one. Based on this one, based on the data booklet, CH3 0.9 until 1.7. Okay, and then this one belongs to CH3, belongs to an alkane. And then let's see the next one. CH2 has the spectrum of 3.5, has a spectrum respectively 3.5 from 3.5. Here, let's see 3.5. 3.5 located will be here. So it is a CH2O, means alkyl next to electronegative atom. We know that in ethanol, CH3, CH2OH, the CH2 is next to the electronegative atom, which is O. That's why it has the chemical shift range between 3.2 until 4, right, in here. And then there is here the spectrum of the chemical shift around 5.1 until 5.3. Let's see in the doublet. It is in the, let's see, based on this one, it cannot be an alkene. Why? Because it is an alcohol. So it is in wider range. Let's see, based on the hydrogen atom, and based on the hydrogen atom, it is in the alcohol between 0.5 until 6. Okay, so this is in the broader range, very wide range. So we find in here, it is between 0.5 until 6. There is, of course, not 0.5 and make big or huge spectrum. No, it is the spectrum is showing a little. This one between 0.5 until 6, there is a chemical shift correspond to alcohol. And then this one in low resolution, we can compare the height in order to determine how many hydrogen atoms there are in the each peak. As we know, below the each peak, we can tell what is the number of hydrogen or the percentage of the hydrogen atoms in the molecule. Example in this one, this is the highest absorption. This one, the middle absorption, and this one is the least absorption. If we compare this one, the least, this one around 2 times to make CH2, and this one approximately requires 1 more. So this one is containing 3 hydrogen atoms. So that is the low resolution. Okay, and then for high resolution, instead of making into one single peak, high resolution will give the shift over ranges, and then the range for different types of hydrogen atoms do overlap. So in some molecules where there is a heavy shielding of the hydrogen nucleus, a lot of electrons in surrounding atoms peaks are shifted beyond their usual range. In such cases, high resolution NMR is useful. This one, high resolution NMR, gives us more information to interpret the results. It appears as one signal at low resolution NMR are often revealed to be made up of a cluster of closely grouped peaks. This is because the magnetic fields generated by spinning nucleus interfere slightly with those of the neighboring nucleus. The interference is called as spin-spin coupling. The exact splitting pattern of a peak depends on the number of hydrogen atoms on the adjacent carbon atoms. Okay, so let me repeat. The exact splitting pattern of a peak depends on the number of hydrogen atoms on the adjacent carbon atom or atoms. On the adjacent carbon atom or atoms. Okay. And then, so it is based on the hydrogen atom on the adjacent carbon atoms. Like in this spectrum chemical shift, here this corresponds to the same as low resolution. The chemical shift the same. The difference in high resolution, there is a splitting pattern. In low resolution, there is no splitting pattern. Let's see the splitting pattern. This one, 3 hydrogen. We know there are 3 hydrogen in it. Okay. The second one, there are 2 hydrogen in it, and then the last one does not contain any carbon atom or only 1 hydrogen atom. This one splitting into 3. This one corresponds to this chemical shift. Why is it splitting into 3? Because the adjacent of the CH3, the carbon atoms, contains 2 hydrogen. We know the splitting pattern of a peak depends on the number of hydrogen atoms on the adjacent carbon atom. The adjacent of CH3 is CH2. So this chemical shift depends on the number of hydrogen on the adjacent carbon atom. Okay, so here this chemical shift 2 hydrogen, that's why it's splits into 3, because the formula is n plus 1. N plus 1, n corresponds to the number of hydrogen atoms. That's why it's split into 3. While this one, the second one, the adjacent, this adjacent doesn't have carbon atom. The adjacent of the CH2 doesn't have carbon atom. It has O. It has oxygen. That's why it splits into 1, because it does not have carbon. So it is considered to be 0. That's why it splits into 1. And then for this one, the alcohol, DOH corresponds to the adjacent carbon atom or atoms. In here, total there are 5 hydrogen atoms. There are 5 hydrogen atoms. But this one, the hydrogen atoms, they are in the same environment. Okay, and this one is this 2 hydrogen atoms. This is also in one environment. That's why there is a splitting 1, 2, 3, 4, and splits. This one also splitting again. Okay, as I told you, this NMR is put in the last subtopic, because the NMR requires the knowledge of the chromatography and then mass spectrometry, also infrared spectroscopy. As I told you, DOH, it is not split, as its hydrogen atom is constantly being exchanged with the hydrogen atom of other ethanol molecules or and any water present. This results in single peak. Okay, this corresponds to the this one, the high resolution So the number of hydrogen atom adjacent on the carbon atom, number of peak. If there is no hydrogen, if there is no carbon atom, there is single peak. It's called singlet. If there is one
Sir, there is a screen in front of you. There's an open window.
carbon, and
About
then
5 minutes.
atom
Yeah.
split into two, which is called duplet. And then
Okay, thanks.
if there are two hydrogen atoms in the adjacent carbon, so it splits into three peaks, which is called as triplet. And then also this one, if three hydrogen atoms on the adjacent carbon, then it is called as quartet. Okay, and then this the high resolution. Now this on the carbon NMR. Okay, this on the carbon NMR. As I told you earlier, NMR can analyze based on the hydrogen 1 and carbon 13. In addition to proton NMR, carbon 13 NMR is another analytical tool used frequently by organic chemists. The vast majority of the carbon atoms in organic compound will be carbon 12 isotope. Therefore, it has no signal on NMR spectrum. An NMR only works with an odd number mass atom. However, 1% of the carbon atoms in any sample of the organic compound will be carbon 13. Each nucleus will interact with the magnetic field applied in NMR analysis, so produce an NMR spectrum, then in ppm, chemical shift. The carbon 13 NMR produces a spectrum with different chemical shift for non-equivalent carbon atoms in a molecule. The typical carbon 13 NMR shifts are shown in the data booklet. Yeah. Also, we have to measure based on the reference of TMS. TMS is at 0 ppm in the spectrum. So the analysis of carbon 13 spectrum is similar to the proton NMR, looking at much different chemical shift to characteristic molecular environment. However, the signal produced in carbon 13 NMR appear as a discrete vertical lines on the spectrum. This we're going to see this one like in this example. This is the an ester. This is an ester. It is an ethyl alkaloid. Okay, so there is a spectrum here, and then there is a CD dissolvent. Dissolvent used to prepare the sample for carbon 13 is CDCl. D stands for deuterium. Deuterium is the hydrogen. Okay. This accounts for small signal near the 80 ppm. It is not at 80 ppm, which can be ignored when interpreting the spectrum. It is caused by an atom of carbon 13 in the solvent molecules. Okay. Okay, here. There is in this spectrum, there is we can see this is carbon. This corresponds to this one.